Welcome to the Explainer. We humans are pretty fragile creatures. There are places we just can't go, but that hasn't stopped us from building machines that can. Today we're diving deep, and I mean really deep, and launching high into the cosmos to understand the absolute genius that goes into building for two of the most hostile environments imaginable.
All right, so here's how we're going to tackle this. First, we'll set the stage by looking at the brutal physics of these two completely different worlds. Then, we'll get into how those challenges shape the actual blueprints. From there, we'll see how these things are built, how they're tested to within an inch of their lives, what they actually do for us, and finally, we'll take a peek at what's coming next.
So let's start with the big, overarching question, the one that drives every single decision here. How on earth do you engineer a machine that can operate day in and day out in a place that would destroy a person in seconds?
And this really nails the fundamental problem. These two environments are polar opposites. For a satellite, you're fighting the void. There's no air, you're getting cooked on one side and frozen on the other, and you're constantly being blasted with radiation. Down in the ocean, though, it's all about pressure. Just immense, bone-crushing force from all directions, plus the constant gnawing attack of salt water trying to eat your machine alive.
Okay, so with those completely opposite battlefields in mind, let's look at the DNA of these machines. Because when you see the blueprints, you realize they are fundamentally different species of engineering.
Building a ship, as you can see here, is just this monumental sequential process. It's a game of massive scale. You start in the digital world with the design, but then you move into this colossal physical construction, fitting it out, and testing everything before this beast is finally let loose on the ocean.
Now, a satellite? It's a totally different story. It's not one giant thing, it's more like an incredibly complex Swiss watch. It's this delicate ecosystem of highly specialized parts. Every single component you see here has a mission-critical job, and if one little piece fails, the whole thing could be lost.
So how do these different blueprints become reality? Well, the whole philosophy behind how you build them couldn't be more different. One is all about brute force and incredible scale. The other is about an obsession with precision and, believe it or not, cleanliness.
With shipbuilding, you're wrestling with giants. We're talking about massive plates of steel, cut with super precise plasma and laser torches. Then they get welded together into these huge sections, they call them blocks, that are then lifted by cranes and pieced together with millimeter accuracy. It's literally like building with the world's heaviest, most high-stakes Legos.
And just look at the hull. I mean, that's not just a big bowl shape. It's a masterclass in physics. It has to be unbelievably strong to handle the forces of the sea, but it's also sculpted to be hydrodynamic, to slice through the water using as little energy as possible. It's a perfect marriage of strength and grace. Now let's jump over to the satellite world, where the engineers are obsessed with the exact opposite of brute force. They're obsessed with being clean. Satellites are built in these special clean rooms where the air is constantly filtered. And why all the fuss? Because in the total vacuum of space, one stray piece of dust or a tiny hair could float into a sensitive camera or cause an electrical short, and poof, your multi-million-dollar mission is over.
So here's the bottom line. The shipbuilder is fighting a chemical war against rust and anything that wants to grow on the hull, using layers of specialized paint like a suit of armor. The satellite engineer, on the other hand, is fighting a thermal war, using this complex system of heaters, radiators, and blankets to keep the electronics from getting fried by the sun or frozen solid in the dark.
All right, so you've built your Titan, but before you send it out into the wild, you have to put it through hell right here on Earth. This is the ultimate stress test.
This quote really says it all. A satellite's first and most violent test isn't even space itself, it's the ride to get there. It has to survive being strapped to what is, for all intents and purposes, a controlled explosion.
And this is the gauntlet it has to run. They literally strap it to a giant shaker table and shake it like crazy to simulate the launch. Then they set off tiny explosives next to it. That's the pyroshock test, to make sure it can handle the jolt of separating from the rocket. And finally, they stick it in a big vacuum chamber and alternately bake and freeze it for days to prove it can handle the temperature swings of orbit.
A ship goes through its own trial by fire too. Before it ever hits the water, every single system, engines, navigation, you name it, is tested and retested. The welds on the hull are scanned with ultrasound to find any hidden flaws. You have to be absolutely certain it's ready for the relentless punishment of the ocean.
Okay, so after surviving the build and all that torture testing, these incredible machines are finally ready to do their jobs.
And in their own unique ways, they both act as a vital lifeline back to all of us here on Earth.
And the scale of this is just hard to wrap your head around. The global shipbuilding industry, it's a massive economic engine, worth over $200 billion every year. That's not just some abstract number. That number represents the phone in your pocket, the clothes you're wearing, the food you eat. Chances are, a lot of it crossed an ocean on one of these ships.
And that really is the key difference. A ship is our physical lifeline. It's like a steel artery carrying the lifeblood of the global economy. A satellite, on the other hand, is our digital lifeline. Its connection isn't a physical one. It's a stream of data caught by a ground station, data that powers everything from your GPS to the weather forecast.
And phoning home from space? Well, it's like trying to hear a whisper from something moving at 17,000 miles per hour. The ground station antenna has to track that satellite across the sky with pinpoint accuracy. It uses this special orbital data called TLEs to know exactly where to point. Then it grabs those faint radio waves, boosts the signal, and sends that incredibly valuable data on its way.
So, we've seen how we build these incredible machines for the extremes of today. But what about tomorrow? In our last section, let's take a quick look at where all of this amazing engineering is going.
And this really is the thought I want to leave you with. We're already entering an era of autonomous cargo ships navigating the oceans by themselves, and we're launching massive constellations of thousands of satellites that all talk to each other. The complexity is just exploding, and it really makes you wonder, what new, even crazier extremes will we have to conquer next?